I've attached an Arducam time-of-flight depth camera and an ESP32 to the Raspberry Pi, and I'm using this for 3D segmentation and distance estimation. And in the rest of the video, I'll show you exactly how I've done that. Also, I just want to say that I've got no affiliation with Arducam and I paid full price for the depth camera. So I got my time-of-flight camera and I ordered this off the Arducam website, and you can also order it off Amazon, and it's a little bit more expensive off Amazon, but you save on the shipping, so it's really much of a muchness. So it comes in this box, so I'm wondering if it's a big camera or it's just got a lot of packing materials in it. Oh, okay, so it's packed in this popping paper here, and then it's just in this little box here. So that's the Arducam time-of-flight camera, and let's open up the box and see what it looks like. Okay, so this is like a 5-volt power cord which plugs into the Raspberry Pi and then into the camera, and then the camera's in this anti-static bag here, and it's got this data cable, the ribbon, and then let's turn it over and see what it looks like. Oh wow, that's amazing. Let me just scroll in a bit. My plan is to use this camera to do 3D object segmentation and distance estimation, where I overlay the image onto another camera. So I've got my Raspberry Pi running through the VNC viewer, which I find is the most convenient way to use it. And I've got the time-of-flight camera connected to the Raspberry Pi. So I'm just going to go through the steps of how to install the time-of-flight camera and view some images from it on the Pi. So first thing we need to do is we need to go to the Arducam GitHub for the time-of-flight camera and clone that on the Raspberry Pi. And the thing I like about the VNC viewer is we can copy and paste stuff from Windows. So I can open the browser on Windows and then paste onto the Pi into a terminal. The clone. So we'll have a look. Okay. Now CD. Okay. Okay, so now what we need to do is we need to run this install dependencies file to install the dependencies for the camera, and that'll install a few things. So now we've installed the Arducam dependencies. We need to do one more thing before we can get it working with Python. And that is to install OpenCV and the Arducam depth library. So if we have a look at this file here, this actually does the install of the OpenCV and the Arducam depth camera. And I don't need to install all these. All I need to do is run this line here, and then I'm all good to go. Okay, so now we can run the Python code to preview the output of the camera. So let's open Thonny, and we'll load the Python script that came with the GitHub repository. So load. Okay, Arducam, example, Python, and this one, preview depth. All right, and now let's run it and see what happens. All right, so just press run. Okay, so I point the camera at myself. There we go. So there's two images. This one here, which is the amplitude image, is like a grey level image. That's the intensity of the infrared camera, and then this one here is the distance estimation. So red is close and blue is far. So if we click on me, it'll show the distance I am away, which is 0.5 meter, will come up on the screen. And then if we click on the background, the distance here is like 3.3 meters away. I'm just going to take you through the demo code from the Arducam GitHub repository, the one that I just ran. So first thing we do is we define the maximum distance, which is 4. So that's the maximum distance is 4 meters away. And then we have this, we can either have it as 4 or 2. So if we have it as 4, it runs at 37.5 megahertz. And if we have it as 2, it runs at 75 megahertz. And now, oddly enough, 37.5 megahertz is 37.5 million pulses per second. And so the time between each pulse is the exact time light takes to travel 8 meters. So, and then I guess 75 megahertz is the time between each pulse is the exact time light takes to travel 4 meters. So the maximum distance for 37.5 megahertz is 4 meters, which is 4 meters there and 4 meters back. And then we get the next pulse. So the first function we have is process frame. So the process frame takes in the depth buffer, which is the camera grabs 2 images, basically a depth buffer and an amplitude buffer. And the amplitude buffer is the amplitude of the infrared signal, like the brightness of it, and the depth buffer is the estimate of how far it is away. And so the depth buffer is decided with the timing, and the amplitude buffer is just the amplitude of the infrared signal. Now, the first thing it does, a little bit of pre-processing on the depth buffer where it sets all the not a numbers to num on the depth buffer. And the amplitude buffer, here these 2 lines are actually quite important. So anything less than 7 in the amplitude buffer is set to 0, and anything greater than 7 is set to 255. So it basically creates a binary image where we have 255 if the amplitude is greater than 7 and 0 if it's less than or equal to 7. And I think the 7 was probably decided in the Arducam labs, but it's fairly important because the further something is away, the more the signal will dissipate. Okay, so if the amplitude is less than 7, then we can't actually judge the distance. So it probably means that it's more than 4 meters away. Okay, so what happens if something's 5 meters away? So we fire off our pulse and it hits this thing 5 meters away and comes back to the sensor. But before it gets to the sensor, we fire off the next pulse. So when this pulse hits the sensor, it thinks that it's the next pulse that we fired off. So something that's 5 meters away, the camera is going to think that's actually just 1 meter away because it's traveled 8 meters when we fire off the next pulse. So 5 meters there, 3 meters back, so it's now 2 meters away. So we fire off this pulse, it travels 2 meters, and whatever it's traveled gets divided in half because it has to travel there and back. So this is quite important. So less than 7 seems to work with 4, but if we use 2, we have to increase this number, and I'll show you how that works. So basically what it does, it takes an AND with the amplitude buffer, which means that anything that's less than or equal to 7 is set to 0. And 0 is the maximum distance. So basically it inverts it. What it does to the depth buffer, it scales it from 0 to 255 and inverts it. So 255 means it's 0 meters away and 0 means it's 4 meters away. What happens is then this returns a grey level image where the brighter something is, the closer it is. Okay, so now we have this rectangle. So this is like a rectangle when you press the mouse on the preview image. It uses this, so it's -4 +4, so it's a 9 by 9 rectangle, which over this rectangle it takes the mean of the depth. So it kind of gets rid of some of the noise. That's how it reduces the noise. It kind of smooths out the spikes by taking the mean, and that's done here. So when you press the mouse on it, it takes the mean over just that rectangle or that square, which is a 9 by 9 rectangle, and then okay, so I get ahead of myself. So when we enter the function, so we have this if name equals main. This is if we run it from the command line, but if we're just running it in Thonny, we don't need this. So the first thing it does is it initializes the camera and the windows, and then it runs this infinite loop, and it gets the depth buffer, which is like the depth image, and the amplitude image, and then it processes the image and it displays the image. Now, and if we press Q, then it exits the loop. So let's also set the max distance to 2 and see what happens. Okay, so that shows me there, right? So now I've got this rectangle. This is my 9 by 9 rectangle, and that's just above my shoulder. So above my right shoulder. So when I press that, it tells me that's about 15 centimeters away. But that's about 2 meters and 15 centimeters away. So what's happened is it's kind of it's sent out the pulse, and the pulse is bouncing back, but before that pulse has reached the sensor, it's already sent the next pulse out. So that's like that should be a 2 in front of there. So how can we get rid of that? I mean, this didn't happen when we did the 4. This didn't happen when we did the 4 just because everything in this room is more than 4 meters away. But the way we can get rid of that red behind me is, let's Q out of there. What we can do is we can increase this. So let's try 27 and see if it gets rid of that red behind me. Because the further away the infrared is, the more it dissipates. So we want anything that's more than 2 meters away basically to dissipate. That will dissipate. So let's try 27. I mean, I don't know if 27 will work. This is just experimentation. And it just, all right, so that's gotten rid of most of that red behind me. See, that's where it was. So that's where the red was. So behind me it was all red. So when I put 27 in there, it seems to now have turned to blue, which is basically the maximum, which is 2 meters away. So I think that's pretty good. Maybe I would up it to 30 because I'm going to process that and get rid of the noise. And I'm going to save these as grey levels and take them onto my desktop here and process them. So I've got the time of flight camera connected here to the CSI port on the Raspberry Pi, and I need to bring another camera in, and there's another port up here, but it's a DSI port, and if I connect a camera to this port, this is a video port, I'm going to fry the camera. The other way to do it is to get a CSI port multiplexer, so you can get like 4 CSI ports, an adapter, but they're a bit expensive. And then the other thing we can do is get a webcam which we can connect to the USB port, but I don't have a webcam. And of course, the next alternative is to bring the image in wirelessly. And so that's what I've done. So I've connected an ESP32 cam up. So I've got the 5 volt, I've got the ESP32 cam just connected to the 5 volt and the ground of the Raspberry Pi. And this 5 volt and ground of the Raspberry Pi is connected to the Arducam time of flight camera. And then I'll just show you. I've got both of these kind of, can you see that? I've got both of these mounted on this piece of perf board at the front. And the thing about this perf board is it is it provides like a natural grid structure so I can get them aligned and in place pretty well, which is something you have to do for a stereo camera. You've got to make sure that they're rigidly in place next to each other horizontally. So we'll fire that up and get the code running and see how that works in the next scene. I've got the ESP32 and the time of flight camera working together, and I'm just taking a naive approach where I'm just overlaying the image from the time of flight camera onto the image from the ESP32, and we'll see how that goes. Alright, so this is the code here, and this is basically the preview code that came with the GitHub repository for the time of flight camera, plus I've added in some code to capture the ESP32 image. So here, this one here sets the resolution on the ESP32 camera, and this sets the quality, and this sets the AWB. The only one I'm using is the set resolution one. So when we start, we just do the normal capture stuff, set up the time of flight camera. This is the URL on the ESP32 cam, and I'm using a static IP for that, and that's in the sketch that I've uploaded. I'll put that sketch on GitHub, and I'll take you through that a bit later as well, just very briefly. So what we do is we capture the sketch, we set our resolution to 5, which I think is 480 times 640 or something like that. The resolutions are up here, it lists them all, and the number, but, so I'm using, 640 times VGA. But I don't know if these numbers are correct for this documentation. So I'm just using 5 at the moment, and we'll see how that works. So I set the resolution, and then I release the camera again, and then I set the resolution again, and then I capture it again. And the reason I have to do this twice is because when I set the resolution, it doesn't always work. It doesn't kind of change till the next time I capture the screen for some reason. So I take a frame from the ESP32 and also a depth frame from the depth buffer, which I process as well. So now I've got my result image, which is my depth image, and my frame ESP32, which is the frame from the image camera, and I resize my result image to bring it into line with the ESP32 image, and then I turn that to color, and I take a weighted sum. So the weights are half alpha, which is the weight of the ESP32 image, and beta, which is the weight from the depth image, and I take a weighted sum. So add weighted just takes a weighted sum of these two images here. I'll put this code up on GitHub anyway, so you can go through it. And I make a combined image, and I display the combined image, and I can save the combined image. And so I can save the combined image, the time of flight image, and the ESP32 image all together. And I'm going to save those and then bring them to my computer and use them to see how I can adjust the time of flight image so that I get the correct overlay, because you'll see it's shifted a bit. Alright, so let me run that and we'll see what's going on. So hopefully this will work. Actually, let me start I at 20 so I don't overwrite images I've already created. Alright, so this is the combined image here, and as we can see, the bottle is shifted a bit over to the left. So that's the bottle, that's the depth image, that's the ESP32 image, and that's the bottle shifted to the left. Right now, if we bring it forward, takes a bit of time. on the ESP32, and then we see it's shifted even more to the left. So I'm going to have to work out a way to, I guess, combine those two. So now with a stereo image.
Dad, can I watch the TV?
So with a stereo pair image, we have two images, and we match the features in each image, and we can get the distance that the object is away. But now we know the distance, so we can use the distance to match the features in the image. And I'll explain all that a bit more clearly on a piece of paper. So I'm just going to explain how I overlay the image from the time of flight camera onto the image from the normal camera. So if we think about a stereo camera, we've got two images, a left image and a right image. Let's say these are not to scale. Left, right. Okay, and we measure, say we take corresponding points in these two images, and we can measure how many pixels across it's moved from the left image to the right image, and from this distance we can then get, from the number of pixels moved across, we can get the distance that the object is away. So now the issue is matching these points. So knowing that this point in the left image corresponds to this point in the right image. And it's very easy for you and I to do that, but for a computer it's a bit harder. So feature matching is like the big problem in stereo vision. Everything else is like just simple geometry. So once we know this pixel distance, then we can get the distance that the object is away. So pixels moved from this, we can get the distance. All right. Now with the time of flight camera, see this is the time of flight camera and this is the image camera. We know the distance here. That's a known. So we already know this, so we go the other direction. So from the distance, we then calculate the pixels moved, which tells us how many pixels over we have to shift that part of the time of flight image to overlay it onto our normal image. And this is much easier because we don't have to do any feature matching. So now our formula for the distance, and I derived this in a previous video, is equal to n over 2 dc over p tan theta plus f. So n is the number of pixels across. So this image is n pixels across, say n pixels. That's the total number of pixels. DC is the distance of the two cameras apart, so I'll just draw that for you. So we've got two cameras, one here and one here, and DC is the distance apart. Sorry, that's not to scale. And then the focal length is F is the focal length of the camera, and this is 2 theta. So tan theta is like basically the view of the camera, how wide a viewing angle we've got from the camera. So now we know the distance, and what we want is P, because this tells us how far across we're moving our time of flight image to overlay it onto our normal image. This is a pixel count because N and P are both in pixels. So we can go 1 on, and now I'm just going to neglect F for now, just set it to 0 just as an approximation. 1 on distance equals 2 on N, P tan theta on DC. So P equals, let's see if I've got this right, let me know if I make a mistake, NDC on distance times 2 tan theta. All right, so we can calculate now. Now I've neglected f, and tan theta, I've just kind of fudged that in my calculation. So I've just kind of set it a tan theta so that for my, when I shift it, it looks pretty good. So I mean, the reason I had to do this is because we're using two different cameras. So if we've got two cameras side by side, both of them are going to have a different f and a different theta. So this is, I mean, this is a bit of an exaggeration. It won't be this different, but the cameras, the geometry of the cameras aren't going to match. So this formula here assumes matching geometry. So what I had to do, I just had to fudge this so it kind of matched. But a better way to do this would be to do, I guess, a manual calibration. So we take the camera, let's say, and then we put an object, say, 10 centimeters away. That's not 10 centimeters, but I'm not doing this to scale. And then we move it 20 centimeters, 30 centimeters, 40 centimeters. And at each measurement, we see how far we have to move the time of flight image. So what we end up with is, we'll end up with something like this. 10 centimeters. I mean, we'll manually shift the time of flight image over, say, certain number of pixels, and just until you get it right on top of the object, 20 centimeters, right out to, let's say, 400 centimeters. And then we'll get, you can just kind of plot points like this, I guess. And then you can do some interpolation. So you can do like some manual calibration. Like I said, I've just kind of fudged this parameter here, just fitted it so that it kind of fits more or less for most of the images that I've got, and it seems to work okay. But because we've got different geometries for the camera, it probably won't work. This formula probably won't be exact. Okay, so we'll have a look at that now. We'll have a look at the shift, and I'll show you the code for that. And then and we'll do that in the next scene. I'm just going to take you through the notebook that I used to develop the code to shift the time of flight depth camera onto the image from the normal camera. So what this does is it just shifts the regions from the time of flight camera over so that they overlay the corresponding regions on the normal camera. And I've downloaded some images from the time of flight camera with the naive overlay that I did, where I just put one on top of the other. So these are the images here. So this is just basically, if we have a look at this, it's just the time of flight image overlaid onto the ESP32 image, and we see that they don't exactly line up. And then this is the corresponding ESP32 image, and then this one here is the time of flight image camera. And to transfer these from the Raspberry Pi to my desktop, just thought I'd show you quickly. I've used this WinSCP program, which is quite good for doing for doing secure FTP. So now I've got all these images to run my tests on. I'll take you through the notebook. So I've just got my display image functions. That's just to have a look at the images. And these are a little bit slow, so I wouldn't be using these on the Raspberry Pi. And do k-means does the k-means clustering on the image, grey levels, where each cluster center, so it returns a clustered image and cluster centers. And each cluster center represents the distance of that pixel away from the camera. So the distance can be calculated like this, but I don't return the distance. And this is when I'm using 4 meters as the maximum distance. If I was using 2 meters, I'd have to change that to a 2. So then the get segmentation takes in the clustered image and the cluster centers, and it returns 3 items, so 3 lists. So the first list is a list of labels, and each label is a representative of how far away that cluster center is from the camera. So it's not the distance, but it's the grey level, and then from the grey level we can calculate the distance using this formula. And then the stats are the bounding box and how many pixels are in each region. And then the other thing this function does, this get segmentation function does, is it gets rid of all regions. It ignores all regions that are less than the minimum region size, which by default is set to 1000, but you can change that. And then the other thing it returns is segmentation masks. So the segmentation masks are just masks where it's Boolean arrays, the same size as the image, where it's true if there's a pixel there and false if there isn't. So this is a list of segmentation masks. So this we can overlay onto the image when it comes time to do our processing. And the other thing I've done is I've ordered the labels from least to most. So it's basically, the ordering is furthest away to closest. And the reason I've done that is they ordered it furthest away to closest is because if I'm doing my processing, I want to do the closest one last if I'm shifting it over, because otherwise the closer object is going to be occluded by the further object, and I want the closest object to be at the front. So if I do that last, if I copy that over last, then that one's going to be at the front. But I'm only doing one object at the moment, which is the closest object. And then I read in my image, so let's just run that for now. So this cell loads the image and it resizes the image to bring it into line with the image from the Arducam depth camera. And then the next cell brings in the Arducam depth camera image, which is the equivalent image, and it does the filtering. It does a median filter. So it gets rid of some of the noise that's in there. And now we run our do k-means and get segmentation, and we have a look at our clustered image. Okay, so this is our clustered image, which is clustered by grey level. So we can see this kind of steps back a bit. And now, so this tan theta, this is like the parameter in the equation that I've fudged a bit to get it to move over a certain distance. So I've just adjusted this experimentally because it's going to be different for both. It's a physical parameter which represents how wide the view is, but it's going to be different for both cameras. So I just do a little bit of a fudge on it, and I found that 0.51 works pretty well in this notebook. Okay, so, and then P is the pixel distance. So the distance is I've calculated it with this formula from the labels, which I've returned up here, which are the labels of the grey levels. And then for each label, I've calculated P, which is how many pixels. To the right, I have to shift the segmentation mask. So now I shift the segmentation mask, and to shift the segmentation mask, so basically I have a mask where some values are true and some values are false. So where it's true, I guess it's just like zeros and ones, and wherever it's a 1, that's where the mask is. And I shift that over, and I could do like a for loop where I iterate through the whole image. So for I in range rows and for j in range cols, and I could do that, and then at each point, if I see the segmentation mask has a true value, then I could just shift that over. But doing this kind of for loop, especially for an image, is really slow. This is something you want to avoid at all costs, especially when you've got a nested for loop. In Python anyway. In C it might be a little bit better. Okay, so I don't do that. What I do is I find my shift for each mask, and then on front of the mask I add on to the left side of the mask that amount of columns, and then I just take the image from there. Alright, so let me show you that actually. Alright, so say this is my segmentation mask now. What I do if I want to shift this over is I add on to the left side, I guess, just a certain number of columns. I mean, that's not drawn very well. And then from there, I just take the left number of columns to correspond to my image size. And this is much quicker than doing a loop. So draw segmentation mask just kind of overlays the mask as a semi-transparent color onto my image. Draw detections draws the box, and annotate distance just writes the distance. And now let's display it. Okay, so the segmentation mask puts the purple semi-transparent mask over the bottle. The annotate distance puts the 14.1 centimeters, which is how far away it is, and the draw detections draws this box around it. And what I've done here is I've only drawn it for the closest one. So basically only if I is the last one in the list, because I'm doing it in order from furthest to closest. Alright, so now I'll quickly show you the ESP32 code, the ESP32 sketch that I've uploaded, and I'll discuss a little bit of an issue that I've had with that, and then I'll put all this together in a Python file, and I'll run it in real time on the Raspberry Pi. So I'll see you in the next scene. This is the code that I've uploaded to the ESP32 cam, and I got the sketch from Random Nerd Tutorials, and I made a few adjustments. So what I've done is I've put in a static IP address. So these parameters here are used to configure the Wi-Fi for the static IP, and I've used 181. So it's always best to use a number either in the high 100s or low 200s to avoid a DNS conflict. And the other thing I've done, the other thing that's in this file, which is probably worth showing you, is the command handler. So the command handler handles requests. This is the command handler. It handles requests from the Python code. So, for example, when the Python code sends a request to change the resolution, and it uses this frame size, and then that's picked up by the command handler. So if we look here, that'll pick it up if it's got like frame size as the variable or quality. So we can basically request to set any of these parameters from the Python code. And then the other thing I wanted to show you is this video capture, CV2.video capture, causes the ESP32 camera to lag a fair bit, and I'll show you that in the next scene. Okay, so this is the image from the ESP32, this is the combined image, and this is the depth image. Now the issue we have with this camera is there's a little bit of a lag on the ESP32. See, so I put my hand there and take it away, and then it gets taken away after, but there's no lag on the depth image. And so what's causing the lag, where the bottleneck is I'll show you. It's in this video capture from the CV2 library. So what this video capture does is it buffers the image, so it puts it in a queue, so it doesn't drop any frames. So when it does its processing, it comes back and it gets the next frame from the queue rather than the latest frame. Alright, so I've updated the code and I've managed to get rid of the lag problem, and I updated the code by using this class that I found on Stack Overflow, written by Ulrich Stern. So I'll take you through the code and I'll show you how I've updated it. The class, I've just basically copied and pasted the class at the front of the file, the video capture class. And then I've gone through my code, and where I had here CV2 video capture, I've just used video capture to use in the file without the CV2, because the video capture includes the CV2 video capture. So if we look at the class that they've defined, that Ulrich's defined, it includes this as a member, CV2 video capture. So then I just have to use the name video capture and create that class, an instance of that class. I've transferred the code from the Jupyter notebook onto this .py file, and I've got this loaded in Thonny, and I've got the Arducam time of flight depth camera and the ESP32 cam connected to the Pi. So I'm going to run this and see how we do 3D segmentation and depth estimation in real time. So I'll press the play button, and there we go. So this is the combined image, which is the segmentation. This is the image from the ESP32 cam, and this one here is the depth image from the time of flight camera. So I'll just move that over a little bit so you can see it a bit better. Alright, so this is giving a bounding box, a segmentation mask, and a distance away, which is quite accurate. So this is really what I wanted. I just wanted to measure the closest object for now. So this is just like a proof of concept. You can add more objects if you want. Alright, so now I'll move this object back and forth, and we'll see that it seems to be working in real time quite well. Now I'll move it back. Okay, I'll move it over here. Alright, so that's working really nicely. And I'll try and track my hand as well. Okay, so it's tracking my hand and measuring the distance and segmenting it very well. So this is exactly what I wanted. But I did want to point out one thing, which is if I tilt the camera up, the ground, or like the desk, gets segmented as part of the object, and sometimes if I tilt it up further, it just gets segmented on its own. So this is something I'm going to have to fix before I put this on a robot. And the way to fix that is to look at the gradient of the grey level. So this is the grey level from the time of flight camera. So if we look at the gradient of this image, especially when it's on the ground, we'll see that actually this is the clustered image that I'm showing. But if we were to look at the raw image, we'd see it'd have some kind of grey level gradient. So this is another feature that I haven't used that I can still use to get the properties of surfaces that are in the image view. So I'm going to have to use this before I connect this to a robot. But I'm going to end the video here, this video, because this is just a proof of concept video, and I'll put that in when I do connect this to a robot. So thank you very much for watching, and I'll see you in the next video. Bye.